Good morning, everybody. Thank you for joining us. My name is Safda Sridharan, and on behalf of Cumulus Networks, I'd like to welcome you to the MLAG Invisible Layer 2 Redundancy webinar. Presenting today will be Scott Emery. Scott is a veteran engineer from networking industry and has worked at 3Com, Grand Junction Networks, and Cisco. Currently, he's working on implementing MLAG and developed software for Cumulus. The webinar will be about 30 to 40 minutes. We'll answer a few questions from the participants at the end if time permits. For those of you interested, you have the opportunity to ask questions during the webinar by using the window marked questions. Simply type in your question and click send. You can also tweet your questions to us. Our Twitter handle is @Cumulus Networks. And with that, I'd like to turn this over to Scott.
Thank you. Good morning, everybody, from a fairly cloudy Mountain View. Today's webinar is MLAG, Invisible Layer 2 Redundancy. And this is going to be a technical talk. So get your propeller beanies on, and we're going to dive into some Layer 2 details, specifically relating to MLAG. So we'll talk about, I'll give a little story about why you'd use MLAG and where it makes sense. And then we'll dive into some of the nitty-gritty details of how it works and how it works differently than a standard Layer 2 network. And then we'll talk about how to configure it under Cumulus Linux and some of the tools that we've got to help analyze and debug any problems that may occur. So let's say that you're an IT manager and you work for a company. You've got it's not a small data center, but it's not huge. And the development manager comes to you and says, we've got this new application. It's going to be the biggest thing in the world. We want to start off with a trial, and we need 20 servers, and he gives you the specs for the servers in the data center. And this is really important. This is basically the future of the company. So you take those specs and you say, okay, well I'm going to over-provision the servers by 20%. I'm going to buy 24 instead of 20, just in case some don't work or some go down. And then you put all those servers in a rack, and you connect them all to a top-of-rack switch, running Cumulus Linux, of course. And then you put redundant connections from that switch to the core of the network. You've got redundant core switches in your data center. And your data center's got redundant internet connections from different providers, just in case one of those goes down, you still have connectivity. You've got redundant power with battery backup and diesel generators that'll keep you going even if your main utility goes down. You've got cooling that's over-provisioned so that if one air conditioner goes out, that the others can at least take enough load that everything stays cool enough to work. You're set. And this thing goes online, and a week later, you get a call from the development manager and says, everything's down. Everything, we can't get to anything. And you're thinking, what in the world happened? Did a meteor strike the data center or something? So you go into the data center, and you quickly find the problem. And the problem was that a power supply on that top-of-rack switch went out and brought down the top-of-rack switch. The top-of-rack switch created a failure domain which included all of the servers. So the basic idea here is that what you want to do is not have that single point of failure take out everything. So, like in everything else you did, you use redundancy. And you install a second top-of-rack switch. And that second top-of-rack switch and how you connect it and get it to work uses a technology called MLAG. Basically what you'll do is in each of your servers, you'll have, instead of one NIC, you'll have two NICs. So those network interface cards, then one of them will connect to one top-of-rack switch, and the other one will connect to the other top-of-rack switch. And that'll give you your redundancy. But it's actually not quite that simple. So I think I sort of just described this as what an MLAG is. It's a lag that goes across more than one node. Now, for terminology, one of the things I'm going to use is the term bond. And the term bond is what Linux uses, and so that's what I'm going to use as the term. A bond is a link aggregation group, an ether channel. There's all sorts of terms for basically taking multiple links and putting them together and making one larger link. But I'll use the term bond for that. And the LAG, as I mentioned, is going to provide you multi-homing for redundancy. So that you have two links now, one to each of the top of rack switches, and if one goes down, the other one's still there. So you've got the redundancy. And since you paid for these two top of rack switches and two NICs and two links, you might as well use them all the time. So MLAG is active-active. It's not that one link is active and then if it goes down, then you switch to a backup link. It's active-active. The other thing is that you can't have, we can't require any special software to be run on the servers. At the other end of the switches, whatever's connected there, we don't know what it is. It could be any variety of Linux or Solaris or Windows or who knows what. All we know is that they're going to have a bond down there connecting to our top-of-rack switches. And that's it. So that's the invisible part, is that these switches really don't, or the hosts don't really know that they're connected to two different switches. Some more terminology is that these two switches are going to be connected via an inter-switch link. And we recommend that that be itself a bond, just for increased reliability. That's a fairly important link between those two switches. You also get a little more bandwidth if you use a bond, twice the bandwidth. One of the switches, those two S1 and S2 at the top of the slide there, one of them will be designated as a primary, and the other one will be designated as a secondary. And I'll get into the nitty-gritty about that. You can let the two switches decide which one is primary and which one's secondary, or you can administratively assign the primary and secondary roles. Then, as far as the servers go, now my example had 24. I've only drawn 5 of them here, just for simplicity. You can see H1 and H5 are singly connected, meaning they only have one NIC, or maybe one of their links has gone down. H2, H3, and H4, those servers have two NICs, one to each of the top-of-rack switches. And they've implemented a bond in H1, or in H2, H3, and H4 to those two switches. So what's it look like from the server's point of view? It looks like this. You have H1 and H5, they're singly connected. You have H2, H3, and H4. And to them, those two physical switches, they don't see. They see one logical switch. They have a two-member bond that's going between their server and a switch. And really, that's the fundamental job of MLAG. When you get down to it, MLAG's whole goal is to make these two independent physical switches look like one logical switch to the outside world. So let's get a little, let's take a deeper dive into some technology here. So LACP is a link access control protocol, and that's what's used to form bonds. That's a standard 802.3 AD, or actually I think it's moved to 802.1 now, protocol. And if we were to simply connect, like in the example here on the slide, H2 to switch S1 and switch S2, H2 would see that it's connected to two different systems. And it would only use one of the links in its bond. The other link would not be used because it's not connected to the same system. So what MLAG does is MLAG assigns the same system ID to switch 1 and switch 2, so that when H2 talks to the two top-of-rack switches, it looks like they're the same switch. As far as LACP is concerned, on H2, it looks like it's the same switch. So another problem that we'd have, if we simply connected things up, is duplicate packets. And also, if a dual-connected host sends out a packet, it would come back to that same host. That's another problem that MLAG has to solve. So I use the term bum packets. I think that's starting to be used more and more in the industry, but it's basically anything that's going to be flooded, a broadcast, an unknown unicast, or a multicast. And I'll go through an example here. Let's say H2 is going to send out a broadcast packet. And who knows how it decides, but it's going to decide to send that packet up the link on the left to switch S1. When that packet gets to switch S1, being a good bridge, S1 is going to flood that packet out all the links except the one on which it came in on. And so it's going to go to H1, H3, H4, and across the inner switch link to S2. When S2 receives the packet, again, being a good bridge, it's going to forward the packet out all links except the one on which it was received. And so the packet will go to H2, H3, H4, and H5. So you see a problem here. When S1 flooded the packet, it went to H3 and H4. And when S2 flooded the packet, it also went to H3 and H4. And it also went to H2, which originated the packet. And so H2 gets the packet back that it sent. H3 and H4 get duplicates of the packet. Both of those are violations of the 802.1 bridging spec. So we've got to take into account some way to fix that. And the way we do that is we introduce a special forwarding rule. When we're operating this in MLAG, packets received on the ISL are not forwarded to dual connected ports. So what that means is that when switch 2 received the packet over the inner switch link, instead of flooding it out all ports except the one on which it was received, it will forward it out all the singly connected interfaces. The dual connected interfaces down to H2, H3, and H4 will not have the packet forwarded out them. And this then eliminates both the duplicate packets to H3 and H4, and also coming back to H2, it won't get the packet it sent. So that's how an MLAG will eliminate duplicate packets and packets returned to the sender. Another thing we have to handle is MAC address learning. Remember, these two switches, we want to act as one logical switch. So an address that's learned on a dual connected port on one switch has to be added to the corresponding dual connected port on the other switch. And similarly, if the address is learned on a singly connected port, then it should be added to the inner switch link port of the other switch. And one of the things we do here is we have a protocol running on each of the switches. This is the MLAG daemon that will communicate amongst the two switches. And it will handle this address learning. And here's an example of that. So let's say that H2 again sends a bum packet up to switch S1. First, again, pick the left link. And so switch S1 is going to learn the packet, learn the destination H2 is on that port there. And I've marked that in the slide with a little red H2. So that any traffic that S1 receives destined to H2 will go down that port and doesn't have to be flooded. But what about S2? When the bum packet is flooded out all ports and S2 receives the packet, it would normally learn that H2 is accessible through the inner switch link because that's where it received the packet. But that's not really what we want. What we would rather have is that S2 would learn that H2 is accessible through its, in this case, it's the leftmost port there going down to H2. So when we're operating as an MLAG, we disable learning on the inner switch link. And when S1 or either of the switches learns an address on one of its dually connected ports or singly connected ports, it sends a message, and using this MLAG daemon, to its peer switch and says, oh, I just learned an address on this port. You should add it to one of your ports. And in this case, H2 will get added to the corresponding dually connected port. And so I have that represented in blue on S2 to indicate that H2 was added manually by S2. It wasn't added because it received a packet with the source address of H2. That's what's done on switch 1. In a similar manner, when H1 is learned on switch 1 as being singly connected down on its leftmost port, it'll send a message across to S2 and say, hey, I learned this address, H1, on this singly connected port. And S2 will then manually add the address to the inner switch link. And in that way, any packets that come in S2 will be forwarded across the inner switch link and then down to H1. So in the end, here's an example of what the learning may look like after all the addresses in this simple example are learned. You can see that H1, of course, got learned on switch 1. Similarly, H5 got learned on switch 2. And messages were sent across so that both those addresses were learned on the inner switch link of the pure switch. Or not learned, they were added manually, represented by the blue. And then S1 was the first switch to receive packets from H2 and H4, and it sent messages across to S2 to manually add H2 and H4 to the S2's corresponding dually connected ports. And then looks like in this case H3 happened to send a packet first up its right-hand link up to switch S2, and S2 then sent a message across to switch 1 to manually add that packet, or that address to its corresponding dually connected port for H3. All right, now I've been talking about the example that I used at the beginning where you have two top-of-rack switches which form an MLAG and act as a single switch represented down to a bunch of servers. But that's not all you can do with MLAG. As a matter of fact, one of the things you can do is switch-to-switch MLAG. So in this case, you could have a pair of MLAG switches connected to another pair of MLAG switches. And in this way, you could extend your layer 2 network beyond just, say, one rack or what's connected to those top-of-rack switches to have a larger domain if you wanted a larger L2 network. And I have an example here. This is how we'd recommend you cable this up. You can see S1 and S2 at the bottom there are your top-of-rack switches that we've been talking about up until now. And they're going to have bonds that go to S3 and S4. And S3 and S4 is another MLAG pair of switches. And you want to interconnect these. And with these 4 interconnects this way, this sort of bow tie configuration, you get the greatest redundancy. If any switch goes down, you'll still have direct connection between the remaining switch in the MLAG and the other pair. From a logical perspective, this is how it looks. It looks like you have a switch at the top, a switch at the bottom, and a bond with 4 members in it between them. So another thing we have to handle is spanning tree. So if we don't handle spanning tree, we'd get links that would be blocked that don't need to be. And so how do we handle this specially? First of all, remember back in the terminology slide I said one switch is the primary role and another switch is the secondary role. So in this case, the primary switch is the one that sends out BPDUs on dual connected ports. So the other switch will not send BPDUs out dual connected ports. And the reason for that is we don't want, in this case, M1 is a sort of mid-level switch. We don't want M1 to receive BPDUs from both S1 and S2. That would be confusing. So it just gets switched. Remember, it thinks it's connected to a single switch. it gets BPDUs only from one, and we say the one that's going to get them from is S1. So that's one thing we do. The other thing is that when BPDUs are received from the root port, they're forwarded, in this case root would be R1, and S1 would receive BPDUs from the root. We forward those across the interswitch link. So they're processed by S1, and they're forwarded across the interswitch link, and they'll be processed by S2 through the interswitch link. A couple other things that we have to handle for spanning tree is that when we receive BPDUs on duly connected links, we also send those across the interswitch link. So let's say that M1 sends its BPDU down the left link to S1. S1 will process that BPDU and act on it just as normally, and it will also send it across the interswitch link to S2. When S2 receives that BPDU, it's going to look at the source MAC address, and it's going to figure out that, oh, I have a duly connected link with that source MAC address. And so it's going to process that BPDU as though it was received on that link. And this is sort of a way that we get both S1 and S2 to know that M1 is connected to it. The other thing we do is that the pure link between the two switches never blocks. And this sort of makes sense because, remember, we're forming a one logical switch with these two switches. And that interswitch link, ISL, really doesn't exist. It's just internal to the, quote, logical switch. Another case that has to be handled is split brain. And if you look at the two pictures on the right, what would happen if the pure link, the ISL, goes down? Right? S2 wouldn't be able to communicate with S1 anymore. But it doesn't know if S1 is absolutely down and dead, or if simply the pure link went down. And its reaction should be different in those two scenarios. In one scenario, S2, if just the pure link has gone down, we have both of the switches still active. And essentially what we want in that case is for S1 and S2 to act as independent switches now. We don't want them to act as an MLAG anymore. If the second case, if switch S1 is totally gone, then S2 is on its own. And it can still keep the system ID and, for spanning tree purposes, the same bridge ID as before. And actually that's what you want, because if it were to change its system ID or its bridge ID, then it would have to, we'd have a topology change, a spanning tree topology change, and the links would flap probably down to the hosts as the bond system ID is changed. So how do we tell between these two scenarios? Well, we allow an optional, or I should say recommended, backup link. So this is shown with this blue line between S1 and S2. So not only can you have the ISL pure link, but you can have this backup link. And the backup link, all it does is sends a heartbeat. And the heartbeat says, yes, I'm alive. So given that, S2 can determine if the pure link is down and the other switch is still alive, or if the other pure link is down and the other switch is absolutely dead. And it can do the right thing then to recover or to not change its state in that case. That backup link is typically the management interface. So each switch has a management port. We label that E0. And you can specify the IP address assigned to that management port as your backup link. And I guess the important thing is that it's a different path than simply going across the pure link, the ISL, to get to the other switch. You'd have to have two failures then to not know if the other switch is dead or if your links are just down. And that's pretty good redundancy there. Okay, so that kind of wraps up MLAG and its use cases and the technology that we have. Now I'm going to go into a little bit about how to configure MLAG and then also how to troubleshoot it. This will be fairly quick. If you have questions that you've thought of up until now will probably be a good time to put them in the question section, so we'll be finishing up in a few minutes here. So an aside here. When I was implementing MLAG for Cumulus, I called it CLAG, Cumulus Lag. And unfortunately, the name stuck. And so as you'll see here, the word CLAG, that's MLAG, that's Cumulus's MLAG. So when you see CLAG, that's just the same thing as MLAG. So how do you configure MLAG? There's two steps. The first step is that all the dual connected interfaces have to be put into a bond. Why are they put into a bond? There's only one reason. It's because that's where, in Linux, LACP is run. So when you create a bond and you put it in the 802.3 AD mode, it'll run LACP. You have to do that even if you have a single slave in the bond, or a single member in the bond. And these two examples show that. They show that on switch S1, we're creating a bond called bond 1. It's going to have a single port, SWP48, as a member. And we're going to give it the MLAG ID of 1. And the MLAG ID here just has to be the same on each switch for a given dually connected port. On switch S2, we're going to call it bond 11. We could have called it bond 1. It's probably best practice to call it bond 1, but I just wanted to make the point that they don't have to be the same name. We don't use the name here to make any association between the two switches. And in switch S2, switch port 4 is connected to the same host as switch port 48 in switch 1. So we put switch port 4 in this bond, and then we give it also the CLAG ID of 1. And the MLAG daemon is going to compare the CLAG IDs of these two bonds along with the partner MAC address. That's the server or the host that these both are connected to. It's going to make sure that everything is cabled up correctly before it forms the dually connected MLAG. So that's what you do. That's the configuration that you have to apply on each of the dually connected ports. The other configuration you have to have is on the inner switch link. So we've created a bond. It's called Pure 6. The bond configuration isn't shown here, but it's basically a couple ports. We put them in a bond, and then we create a VLAN subinterface of that bond. Now I'm using VLAN 4000 here. So you can see on the left, Pure 6.4000. That's VLAN 4000 off of this bond called Pure 6. And that VLAN just has to be not one of the VLANs that is used in the bridge. So it's a VLAN that's not used anywhere else, basically. We'll give that VLAN subinterface an IP address, and we recommend a link local IP address because the interconnection between the two switches, this ISL, is always a single link interface. There's nothing in between it. And so we can use a link local address. That way, again, this traffic won't somehow get outside of that link. We need to define two things at a minimum. The first is the peer's IP address. So that's what this switch will use to contact the other switch. And you can see that we used 169.254.0.2 on the left switch as the peer IP, and that is the IP address we gave to that peer link. And same as vice versa. The right switch uses the left switch's IP address as the peer IP. The second required parameter is the system MAC address. This is a MAC address that will be used on all the bonds so that the partner, the servers, will see them as the same system. And also this will be used as the bridge ID in spanning tree. So we recommend that you use an address in the range, and I show an address here. The first 4 bytes of this address, 44, 38, 39 FF, should be fixed. And then the last 2 bytes can be anything you want, but they have to be the same on both of the 2 switches in an MLAG pair. Cumulus has reserved the 64K addresses for use in MLAG. So you can be guaranteed that any address that starts with 44, 38, 39 FF will not be programmed into any vendor equipment anywhere in the world. The third thing you can optionally specify here is the backup IP address. And this is probably the management interface IP address. And it's shown here that switch S2's management IP address is probably 192.168.1.101. And this provides that backup link I was talking about to handle the split brain versus dead peer situation. And that's it. Once you configure that, you're able to bring up an MLAG. And once you bring it up, how do you know it's working? There's a couple tools, and I'll just go over a few of them here. The first one is CLAG control, CLAG control. And this is a tool that interfaces to the CLAG daemon, or MLAG daemon. If you simply type CLAG control, you'll get a status. And you can see on switch S1, I type CLAG control, it says that the peer is alive. Here is the role of the peer. You can see the peer is the primary. We are the secondary role. Those items there, the priority and ID. The priority is what determines who is the primary. And in this case, the priorities were the same because they weren't assigned. And the default priority is 32768. And so the tiebreaker is the ISL's MAC address, the MAC address of the interswitch link. And you can see that the peer had the lower MAC address, and so he won. If you want to actually specify which switch should be the primary and which should be the secondary, just assign the priority lower on the one you want to be the primary. And you can do that dynamically using the CLAG control command, or you can do that in the SE network interfaces statically by doing a CLAG-D-priority under the interswitch link interface. And then it shows we have a backup IP. We have it shows the system MAC that was assigned, and also it shows all the dual connected ports. And in this case, we have 5 servers that were dually connected in this particular setup. And it shows you the CLAG IDs and the names of the bonds on each side, switch 1 and switch S2. And finally, we've got, that didn't come out quite right. I apologize for that, but syslog contains logging information about the MLAG daemon. And you can see here it's logged that it came up, that its role is secondary, that it loaded the configuration, it communicated with the peer, and it did the peer exchange of initial information, and then you can see all the 5 bonds became dually connected. The CLAG IDs were right, and they were both connected to the same partner. Any errors or any unusual conditions will also show up in this log. You can't see it because of the way the formatting of the slide goes, but what I did was I did a grep for CLAG-D in /var/log/syslog. And that concludes the presentation I had for MLAG. And I think we can now open it up for a few questions. We still got time.
Thank you, Scott. It was a great presentation. We have tons of questions from the attendees, and we'll try to get through as many of them as possible. And if we run out of time, we'll try to address them offline. One of the first questions is from Ian, which the question is, are there any caveats or limitations to using IPv4/IPv6 dual stack with MLAG?
So as far as MLAG goes, So I'll answer that in two ways. First is that the MLAG operates at layer 2. So as far as the hosts go, if they're running IPv4, v6, v20, or whatever they come up with, it doesn't care, since it's only operating at layer 2. Now, the communication between the two MLAG daemons on the two switches is using TCP/IP, and it uses IPv4. I showed IPv4 addresses and so forth. It wouldn't be a stretch to improve it to be able to use IPv6. We just haven't done that yet. But as far as the general MLAG operation, it doesn't care if the layer 3 protocol is v4, v6.
Next question. Is there anything special you need to do for single home host? Asking due to other vendors don't support single home devices on MLAG switches.
Yeah, there's nothing special you have to do. In those cases, if you know they're singly connected, you wouldn't even put them in a bond. You just have them singly connected. You'd add that port to the bridge, and you'd be good. There's nothing really you have to do specially for singly connected hosts. I'll mention that a dually connected host can become singly connected if one of the links breaks, or they have you disconnect a cable from one of the dually connected links. And in that case, it's just a dually connected host becoming singly connected. There's no configuration or anything you need to do there either.
Next question. Is the ISL just a normal Ethernet port, or is it a stacking mode port like the Broadcom high gig links?
Yeah, so we haven't used anything proprietary here. So that's just a normal Ethernet port, or a couple of Ethernet ports if you're going to put them into a bond like we recommend.
The next question is, we've had problems with MLAG and IPv6 on Juniper devices. Have you seen a problem with CLAG and IPv6?
Again, as far as the data traffic goes between the servers and just talking to the rest of the data center or amongst themselves, MLAG is totally, it doesn't care. It operates at layer 2. If you wanted to configure the communication between the MLAG daemons using IPv6 as opposed to IPv4, again, we don't support that yet. But as I said, it wouldn't be a stretch to be able to allow that.
Next question. In STP over MLAG, how does the secondary switch maintain the STP state, since primary switch sends the BPDU on dual connected links?
Right. So I probably should have gone into a little more detail on this. Our model is that each of the switches is running its own spanning tree protocol. We don't have one protocol running on one of the switches, and the other switch is sort of a dumb switch, just shoveling packets back and forth to that one master. So they're both running their own independent spanning trees. And what I was describing there was the way that each switch gets the same view of the other switches. And that's why I was saying that the packets like from a root port or from dually connected interfaces are going to be shuttled through the ISL so that the other switch can get the same view or the same state of the world. I hope that answered the question.
Thank you. The next question is it similar to regular lag?
So from the server's point of view, it's exactly the same as regular lag. They don't even know that you're doing this MLAG thing. That was the invisible part of this whole thing. From the switch's point of view, it's similar to lag, except it's spread across two switches. In other words, you got one port on one switch and one port on the other switch. They're both forming a lag, but as I mentioned in the presentation, there's some extra considerations that have to be taken into account to handle the learning and the forwarding and spanning tree.
Next question. How does this eliminate the need for a protocol like PVST+?
Eliminate. So spanning tree is going to run on top of this MLAG. As I mentioned, we're going to have spanning tree running on both of these switches. And so it doesn't, I don't think, eliminate the need for spanning tree. It's just that we want to make, from the outside world, both these switches look like a single switch.
Thank you. Next question. Do you recommend connecting 3, 4, and more pairs of switches this way?
Okay. So currently, our MLAG only supports 2 switches. And quite frankly, you're getting a little crazy if you get to 3 or 4. Particularly like the servers, I wouldn't expect you to have more than 2 NICs in the servers going up. And you're really getting crazy if you need triple redundancy or quadruple redundancy between your servers and your switches. So we haven't supported more than 2 switches right now.
Thank you. Another question is, if the ISL is a bond, in practice, isn't that sufficient redundancy to prevent split brain?
Yeah, I mean, you could think of it that way. The problem would be is that both of those links go down. You have no idea between that case and the case of the switch, your partner switch dying, because in that case both of the links would go down also. But you're right. There is, because it's a bond, it's got multiple links. The likelihood of everything in that ISL going down is pretty low.
I think there's a follow-up question on that. Must both switches be identical, same brand and model?
So both the switches don't have to be the same brand and model. They both have to be running Cumulus Linux. So that's something to point out here is that since there's no standard for MLAG, you can't take a switch from one vendor and a switch from another vendor and try to put them together, in a single MLAG. Both those switches have to run in the same operating system. However, what you can do is you can have 2 switches from one vendor form an MLAG, and 2 switches from another vendor form an MLAG, and interconnect them like I showed in the switch-to-switch MLAG. That will work, and we have tested that.
One other question is that if the uplink from switch 2 into the network is down, does switch 1 have data from its uplinks over its local ports and the S2 ports?
So I'm not sure I can answer this question. Are we assuming that I'm going to assume that the uplinks that you're talking about here are layer 2, and they're part of the bridge. And what would happen there is just like they would be basically an MLAG pair going up. And if you lose one, what would happen is the connection to the rest of the network would become singly connected. And any traffic, so when you're singly connected, any traffic going up out of those uplinks would then go through the interswitch link from the peer switch or go directly up on the switch that has the active uplink. If the uplinks are layer 3, they're routed to the uplinks, we have a technology called VRR, which is sort of a play on acronyms. It's VRRP without the protocol. And you can look into that on our webpage and our documentation at cumulusnetworks.com.
Thank you, Scott. I think we've run out of time. So thank you, everyone, for your participation. We hope you found this presentation about MLAG useful. We got a lot of questions, and there are still some of the questions that we couldn't get to, and we'll try to answer them offline separately. Please tune in to our next webinar, which is using Linux for your entire rack, which is on May 27th. And that's it for today. Thank you for your time, and we look forward to seeing you in our next webinar.